thing that we're going to do once we are done finding the tie line that will exceed that will pass through the feed point, the next thing that we're going to do is to extend the tie line to both the leftmost and rightmost part of the diagram to find for the delta E min and the delta S min values. So from your discussion in or your readings in your Ponchon Savarit, books or in your books related to Ponchon Savarit method, the delta E corresponds to the difference point in the enriching section, while the delta S corresponds to the difference point in the stripping section. So I would like to write that one here. Okay, it might be a useful information that you were not aware. Okay, so the delta E is called the difference point. So it's the label of the point. Difference point in enriching section. Enriching section. And the delta S is the difference point in the delta S is the difference point in the stripping section. Okay. So we are looking for not the delta E, not the delta S, but the delta E min. So the minimum value of the delta E. Okay, and we can only do that by extending the tie line that we have created here. Okay, until such time that it will touch, okay, through, or it will touch the calibration that I have done here. Okay, yeah. Okay, I think I forgot something. We need to also actually plot for the distillate and the bottoms values, because we cannot just rely on this. There must be an intersection. Okay, that's what I meant. The intersection of the extended tie line to the value of the distillate. Okay, I think that's something that I missed. Okay, so we need to copy paste the point over here so that we won't, you know, spend much time. So I will be creating many points at the side. So I think the distillate mole fraction is, oops. Okay, I think that's an error in the, okay. The distillate mole fraction is 0.98. So I should place my right here. Okay. So if you ask me, why should you place the distillate point in the saturated liquid? Remember that the distillate composition is already a condensed. It's the distillate is already a condensed form of the product. So you should not be placing it on the vapor line because it's already condensed. So the enthalpy associated with it is already in the saturated liquid. Okay, so what we're going to do is to extend, okay, another line. Oops, I think, okay, it's somehow difficult. So I will be extending a line over here, but oops, okay, we might be, pushing it further. Okay, yeah, I think that's enough. We just have to make sure that I'm extending just the right length. I will be increasing the weight as usual to make sure that yeah, and then I will be creating another an extension of this tie line. Okay, and then we are going to look for the intersection D. Okay, control D and then extend. Okay, it's somehow difficult in doing this by Microsoft Word. As far as other YouTube videos are concerned, I have not seen them do this yet. Oh, it's not yet extended, so I need to extend more. All right, so I have found an intersection. So remember that you have to extend the tie line and intersect it with a vertical line starting from the distillate point. Okay. So yeah, that's the delta E min. This is your delta E min. Okay. Oops, I think this is located. Okay, wait, can I cancel? I need to place it at the front. Yeah, it's already at the front. Okay, bring forward. Okay, so that it can be here. Okay. I hope I'm doing it correctly. It's somehow challenging if I'm going to use Microsoft Word to plot. Okay, but yeah, we can do this. Let's color this. Okay, just this one. Okay. And then we have already found for the delta emin. We have found the delta emin already. Okay, the challenge is for us to determine what is the value of delta emin because we're going to use that in our calculations to determine the value of R min. Okay, so the delta emin, okay, the value of this one is remember, okay, I don't want to dig deeper on like the calculations or how to estimate the value because I believe you are capable of doing it already. But I would just like to emphasize that the calibrations that where I base it from is this one here on the left side. If you notice, the calibrations or the steps are in there is an addition of 5,000 for every major step that you do. Okay, so if you are going to if you're going to continue the increase of the values, if you have here 45,000 kilojoules per kilomole, this will be 50, 55, 60, 65, and then 70. So this will be 65 something. Okay, so this will be 67 or something. So again, 45, 50, 55, 60, 65, and then 70. So it is up to you as apply your interpolation scales. Okay, locate where is this. Okay, if you're doing it manually, I think you should be measuring the ratio of this line, the from here to here, and then the ratio of this line from here to here, so that you can know what's the corresponding value of that one. But remember, this is 65,000, this one, and then this is 70,000. Okay, from my calculations or from how I read it in my manually created drawing here, the value of my delta E min, okay, the Y value of my delta E min. So, okay, because the delta E min is a point. Remember that delta E min is a point. Delta E min is a point. Okay, so that means we know that for the delta E min point, the X value is 0.98, right? That's the distillate composition. Okay, so let's go back to the drawing. It's X8, right? It's XD, right? This one, and then extend. Okay, that's the X value. But the Y value is the value of the enthalpy. So the Y value or the corresponding value of the E min here, this is from my reading, okay? Your reading might be different from mine. 65,227.27. So it might be too extra on my part to really have a 0.27. But yeah, anyway, that's how I calibrated it. But it depends on you. Okay, I think it's not anymore necessary, this value, because if you look at it, um, if you look at our drawing, uh, we already reported everything in ones digit. I think you can just report it crudely as 65,200. Okay, I think that would be much better. Okay, so yeah, that's the value of my delta Emin. Okay, it's somehow confusing because usually most books already refer the delta Emin term as the y value. Okay, but usually it's also confusing because the delta E and delta S are actually points, like point labels. So that's why I emphasized here that the y value of delta E min is what we are actually referring to. Okay, but please be reminded that we are going to use the y value of delta E min and the symbol of delta E min interchangeably. Okay, so if I write delta E min as part of the equation, it is already assumed that um, what is asked here is the y value of the delta E min, which is the 65,227.27 kilojoules per kilomole. Okay. All right, so we are already done, or we are finished with the part wherein we can determine the value of delta E min. Okay. For the delta S min, it's actually not that relevant for now. But if you want to know how to get it, you can actually just extend. Okay. Probably your instructor will require you to determine the value of delta S min. So it's actually easy because you just need to extend. Okay, this tile line over here. Okay, create another line. Okay, touch it. Okay, it's actually easier in doing it manually. Okay, was I able to? It's barely accurate, but it doesn't really matter. Okay, and what we're going to do is just to hold it and then go downwards. Oops. Extend, extend, extend. Okay. I need to. I should not let go of the shift because I don't want to. Okay, we're here. Okay. Okay, I just extended here. But don't forget, okay, aside from that one, we need to locate the value of your XB first, or the mole fraction of your bottoms. Okay, duplicate. Let's locate the value of your bottoms. It's actually 0.04, right? Am I correct? 0.04. Okay, it's 0.04. So it must be located here. 0.01, 02, 04. Okay, here. There. And what you're going to do is to do the same thing that I did in the other side in the distillate. I extended a vertical line here. So I must also do the same thing in the left side. Okay, so let me zoom out and then extend it on the left side. Oops! Oh my gosh, I moved the graph. Okay, no. No, okay. Here. Okay, I hope I'm doing this right. Okay, that's okay. Okay, I'm very lucky I was able to get the intersection right away. So that's the delta S min here. That's the delta S min, but it's not actually super relevant. It's not actually relevant in the calculations. So that's why most people don't really look for it. Yeah, but for the purposes of symmetry, I'm actually conscious um, in terms of how the diagram would look like. That's my personal biases when drawing Ponchon Savarit diagrams. Okay, so we're now done looking for the delta E min and delta S min. Okay, so the next step would be to okay. There must be something wrong in my drawing, but I think I need to move this up. Yeah, I think I need to move this up. Okay. Moving this up will not affect um, the measurements, okay? So don't worry. I also need to change the color. It's actually closer to black, so it doesn't, you know, have a distinctive. Okay, this one. And then this is, let's color this brown. Oops, they're actually different colors. Okay, so that's what took everything long. Sorry guys. Okay, yeah. Okay, so that's it for the delta E min and delta S min. So I have the value of the delta E min already. Okay, the next step is for me to, okay, we need to determine first the minimum reflux ratio. Okay, so solve for the minimum reflux ratio. Okay, so the formula for this one, okay, so the relationship between the reflux ratio and the delta E is this. Okay, let me give you a formula. The formula is, okay, this is the reflux ratio is equal to the difference of delta E minus HV1 and then HV1 minus HD. Okay, so if you ask me, that is the reflux ratio, that's the delta E. The HV1 is actually the enthalpy of the vapor form of the distillate in the first stage. Okay, that's the enthalpy, the moment the stage number one at the topmost released its vapor, okay, containing the distilled product, but in vapor form. If you want to locate the value of HV1, it's actually here. This is the value of HV1 here. Remember that that is the value, that's the, it has the same molar composition as the distillate, but it's just in vapor form. That's why okay, it lies at the same vertical line as the distillate, right? Because it actually has the same vapor composition as the distillate. It's just that it's in vapor form yet. It was not, it has not passed the condenser yet. That's why it's in the vapor form. So if you want to know the value of this one, okay, you have to extend the line towards the left side so that you can read. So it's around 30 something. I think 31,000. Yeah, it's around 31,000. And then the value of the distillate, okay, it's probably okay, 5,000. Okay. So from my calculations, it's not really super clear here. It's not equal to 0 because the enthalpy at the value of enthalpy the concentration at the concentration that will make the enthalpy 0 is 1, or pure benzene, but it's not pure benzene, right? It's 0.98. So I will put a label here. Okay, just a label. I can't actually draw because if I draw it, if I write some drawings here in the Microsoft Word, there are some errors. So this is the value of your HV1. Okay, oops. No fail. This is the HV1 and this is the HD. Okay. Yeah. Remember that my HD is not equal to 0, okay? It's just the, the very heavy, it's not really accurate here in the diagram. But according to my calculations, the value of my HV1, oops, sorry. The value of my HV1, okay, is equal to 30,909.09. Okay, so don't bother the two decimal places because I just I just base it on how I calibrated it using my ruler. And then HD, okay, but the actual significant figures are, it doesn't include it. It doesn't include the decimal points. My value of HD is 227.27. 227.27. Of course, the units are in kilojoules per kilomole. Okay. If you wonder, I have already introduced this to you, but the formula I introduced is not delta E min. Okay. Where's delta E min? Okay. Um, okay, the pattern for the formula is just for delta E min. It's just similar to the one above. Okay, if you want to look for the minimum reflux ratio, you just copy the formula above, but this time use the parameter delta E min instead of delta E. HV, comma 1, and then HV 1, and then minus HD. Okay, so that is your delta, that's your R min. Okay, now let's solve for the value of R min. Okay, so I think we have already the values for delta E min, HV1, and HT. For the delta E min, that is 65,227.27. Okay, and then minus HV1, that is 30,909.09, and then we have 30,909.09. Okay. Do not be bothered by the decimal points. Okay, it's actually my personal choice to do this, but actually you don't need to write the decimal points because the values are already big. Okay, we are not really talking in putting exact um, measurements. Okay, if you're going to solve the value of R min for this one, you will get, okay, according to my calculations, 1.1185. So it's around 1.12, the minimum reflux ratio. Okay, so we have already the value of the minimum reflux ratio, which is 1.12. And then the next thing, okay, we're done with the minimum reflux ratio. Let's now proceed to the next step. Solve for the recommended value of R based on the value of R min. So we're going to solve for this one. Okay, so let's solve for the recommended value of R. It was stated in the problem that the reflux ratio is 1.3 times the minimum. So we're going to solve for R. R is equal to 1.3 times the minimum reflux ratio. So that means 1.3 times 1.12. Okay, that will be equal to 1.3 times 1.12. That will be equal to 1.456, or okay, you can just use 1.46. Okay, so yeah, that's the value of our reflux ratio that we're going to use. Okay, next is using the value of R, solve for the value of delta E. So this is the time that we're going to use the equation above, this one, to solve for the value of delta E. Again, why is it very important to solve for the value of delta E? Because the delta E will help us, or the delta E value or the Y value of the delta E will help us in the pivoting for our stepping off. When I say pivoting, that's actually the difference point or the pivot point wherein all operating lines meet. So it's a very important number when you talk about graphing Ponchon Savarit. Okay, this is where the difference point is where all the operating lines meet. Okay, so remember that one. Okay. So if you have a value of 1.46, and then your delta E is unknown, you can use your calculator to, solve for the value of delta E. The HV1 is 30909.09 over 30909.09 minus 227.27. Okay, for this one, okay, delta E. So, you can just use your calculator, do the algebra. Okay, if you are going to solve for delta E, my answer is 75,523.52. Okay, so don't bother too much about the decimal points, okay? You can just have a crude, it can just be 75,500 actually. Yeah, it's actually fine with that one, but I just preferred to, be specific and um yeah, with my calculations. Okay, so you have already the value of your delta E. Okay, this is again, guys, this is the Y value of delta E. Specifically the Y value of delta E. Okay. It has actually a variable. It has a variable here. The variable for this one is Q prime. Okay, that's the variable that I'm going to use later. Okay, yeah, that's Q prime. For this one, we can just call this as the Q prime min. Okay, yeah. Okay, so we're going to plot that one. So what we're going to plot is delta E point. Okay, the value of your Q prime or your Y value is 75,500, and then your X D, your X corresponds to 0.98. So of course guys, the point over here, I really placed the point here. The XE point, it's called a point. Okay, it's a point. So of course the X value is similar to the distillate, of course, because it should be found in the distillate vertical line. And then the Y prime is 75,500. So it's greater than the one that you got here. This is 65,000, but this is 75,500. So let us plot it here in the drawing. Where is it located? If we have 75,500, so remember this is 45. So 50, 55, 60, 65, something, and then 70, and then 75. 75,000 something here. This is 80, so we can just place it here. Okay. So the value of your delta E min is placed here. So that's the Y value, and the X value is of course your 0.98. So you can just locate it. 65, 70, 75 something. Okay, here. Okay, again, it's just purely estimation, guys. So I can't really, locate it exactly in the Microsoft Word. Okay, so that's the delta E min. What now? Okay. The next thing that you're going to do, okay, did I mention that here at the top? Okay. Yeah, I think we're done with that part. That will be our pivot point later. Okay. What you need to take note is that the feed point line or the feed line, okay, is where the delta E line over here and the feed point will pass through. So delta E, the feed point, as well as the actual delta S value. Okay, so you would expect that the delta S will be here at the bottommost part. So I think this will be lacking in terms of the calibrations. Okay, it's kind of long, really. Okay, so let's try to plot the feed point line first. I'm going to write that here. So for the value of the feed point line. So okay, I have done here. I'm done here with this part. And then yeah, I think we can just plot the feed point line. It's not really necessary. Plot the feed line. Okay. Connecting the feed point and delta E. Okay. Yeah. All right. Okay, and I think we can just also connect it to delta S. Yeah, I think we can just connect it to delta S. Oops. Okay, apologies. Okay, so how are we going to do this? Okay, easy. You just get a line, and then from the delta E, you find a way that you intersect the feed point here. Okay, and then find a way that, okay, I think it's not practical to there. Okay, I'll make this red, I guess. Yeah, and then extend the width. Okay, there. I hope it was able to pass through the feed point. So the delta E value and the feed point should be, they should intersect. And then also, aside from the feed point, the delta S should also be part of this red line over here. So we need to extend this line. Okay, and touch it to the vertical line for the bottoms. And then that's the point where we can see that we can also locate for the delta S. Okay. Here. Okay, it really takes us a long time to plot. And all right, yeah. So it's actually lacking. It's not really that lacking. We can still read it even though, okay, here. This is our delta S. Okay, remember, this is our delta S. This is our delta E. Okay. So yeah, okay, we are now done drawing the feed line. Okay, we're now ready in the stepping off process. Okay, so how are we going to do the stepping off for Ponchon Savarit and determine the number of theoretical stages? To do this, oops. To do this, the first thing that we're going to do is to okay, use the XY diagram at the bottom part to make a tile line that will complement the HV1 here at the top. Okay, so what I mean is, like, in one stage there is an exiting vapor with a composition, and then there's also an exiting liquid with a certain composition. We already have the composition of the vapor exiting, which is here in this line over here. This is the composition of the vapor exiting, and that is 0.98. But what about the liquid composition exiting that stage? So how are we going to determine that? To determine that, we're going to extend the tie line. And we're going to extend the vertical line at the bottom and touch the 45-degree line. And then after that, we're going to create a horizontal line. So this is actually the reverse of what we did. earlier. Okay, let's make this red to make it clear. And then last but not the least, after the vertical, horizontal, vertical, and then we're doing the vertical again to touch it here. Okay. So the reading is, I think, 22, around 0.95. Okay, so the vapor phase composition that, the liquid phase composition that exited the first stage is around X1 is 0.95. Okay, that's what it meant. That's what it meant here. Okay, so to make a tie line, okay, what are we going to do is to, again, connect. No? Connect this point over here and connect it to this one. Connect it here. Okay, so that's the first tie line. And the first tie line corresponds to the first equilibrium stage. So, yeah, that's the first stage. But we're not done yet. That's still the first. Okay, so, okay. Next is to locate the value of the equilibrium, not equilibrium, the upper, we're going to locate the point where the vapor composition of the next stage, okay, is located. So we're going to do that by extending this point over here to the operating line, creating an operating line by making or extending a point over here towards the delta E. Okay, I think I should place here delta E so that you won't be confused. Horizontal. Okay, delta E, insert symbol. It kinda takes a long time if we're going to use Microsoft Word, but we have no choice. Delta. Delta E. Okay. Um, oops. No outline. Okay, that's delta E. Okay, no fill. Okay, here. So we're going to create an operating line from that point over here up to the delta E. Okay, so actually the purpose of delta E min is just to locate the value of R. It doesn't do much in the actual stepping off. Okay, there. Okay, I'm coloring this brown. Okay, weight is here. Okay, let me just use a weight. Okay, so we're done with the first operating line, but we're not done yet. Okay, we still have a long way to go. So what now? Okay, what next? Okay, we have located the point where the vapor composition of the second stage exits. The vapor composition of the exiting vapor stream in the second stage. Okay, so let us do the same thing again. Okay, extend. Okay, go down. Okay, go down the vertical line. Use shift, or if in actual setting you don't use shift, just use ruler. Okay, and then this one over here, and then extend. So vertical, horizontal, touch the equilibrium curve, and then go up. Oops. There. Okay. And then the moment it touches this part, okay, that's the proper location. Oh, why did I extend it here? Okay, no, it's not correct. I should not extend that there. You can't go down. You should just make sure it's straight. Okay, and then make the operating line from this point to this point. So what I'm going to do, it's really tedious. Okay, but Control D. Make the same operating line. And then, okay, put it here. Alright. Okay. Again, guys, the purpose of doing the operating line from this point to this point is for us to locate this point over here. Okay. Oh, we have not placed the tie line yet for the second. From this point to this point. Yeah, there should be a tie line. So that will be our second stage. See, what makes it look effortful is the fact that I'm doing it via Microsoft Word. So I would really encourage you to do it manually. Okay, not do the same thing as mine. Okay, so we have located this point already. This is the Y3. Okay, we have to locate for the X3. Okay, so we can do that by doing another thing again, another round of the tie line. In order to make it, okay, never mind. Let's just continue it. I plan to delete, but it will be difficult to delete because all the lines are most of the tie lines, most of the guidelines that we're using are so thin. The weights are so small, so it's difficult to locate. Okay, vertical. Touch it to the 45-degree line and then touch it here. Okay, and then we're going to touch that here at the top. Oops. So I'm going to cut the video. I'm going to like cut it and fast forward to the point wherein I will cross over the feed line because there's a different approach to this one. Okay, so I have found this one. Okay, create a tie line. I'll just copy paste the tie line. That the violet lines are the stages. Okay, those are the tie lines. There. Okay, so let's do it again. Another operating line. I'll just copy operating lines. I won't create again. Okay, there, and then touch it here. Okay. All right. Okay, so the process continues. Okay, so I will be cutting the video and I will continue the whole process and proceed. The video will proceed to the part wherein we're going to cross over after this feed line, the red line over here. That's the actual feed line.